tricky topic. And so it's good to read it, but it's also good to see it, and then you can read it again and just see what's up. So, oh, you can't see my screen.
No.
I'm going to turn our faces off. Actually, no, I'm not, so I can still see you. Okay, can you see my screen now?
Yes.
All right, so this is the intuition. And I'm recording this. This is also going to be available to look at. So you don't have to take any detailed notes unless you just want to. Okay.
Right.
So ask any questions you have. So here's the idea. Suppose we take a group like this one. So it's given by, it has elements 1, 2, 3, 1, 2, 3, 4. And then we know how to add, right? And so n plus m inside this group is just n plus m mod 4 as integers, right? And that's what sorry, mod 5.
Yeah.
Thank you. I saw your face. So that's what the structure of this group is like, right?
Yeah.
Okay, and we can make a multiplication table and all that fun stuff. There's another way that we can represent this group. So one thing we can do is to take a generating set. So you learned what generators are before, right? In your other algebra.
Yeah.
Okay. So what is a generating set for this group? Just give me a set that generates this group. I actually want to call it X.
Do we include the identity in the generating set?
You can, but the identity alone can't because
Generate it.
because you know 0 plus 0 plus 0 is always going to give you 0, right?
Do they all generate this set?
So you can take the whole thing, as a set, but for example, yes, you can take 2 because 2 plus 2 is 4. 4 plus 2 is 6, which is 1, right? 1 plus 2 is 3. 3 plus 2 is 0. So that's everything.
Yeah.
So you can take 2. You can take anything.
Yeah.
Because 5 is prime, you can do.
Yeah.
Let's just take a simple one. Let's just take
1.
1. Okay. So what we do is we take the free group, and I'll talk about what that means in a second, the free group on 1. Gonna write it. And all it is, it's this group that has elements, what I'm going to call the empty string, right? It has 1. It has 1 times 1, which is 1 squared. Now, this isn't like the integer 1 anymore, okay? This abstract symbol.
Yeah.
And 1 cubed and 1 to the 4th and so on. It goes on forever. Again, these are symbols. This is not, I'm not going to say 1 to the 4th is 1 because we're not talking about integers anymore. It also includes, you know, inverses. So 1 to the -1, 1 to the -2, etc.
Yeah.
This is this formal construction that I'll define in just a second. So there is a homomorphism that goes from this free group on the symbol 1 to Z5.
Yeah. That
takes the symbol 1 to the class of 1. It's not really a class yet, to the element 1 inside Z5. Now, what's the kernel of that homomorphism?
1.
No.
Or it takes it to
So there's 1. 1 squared would get mapped where?
Like the empty word. Oh, 1 squared would go to 2 or 1. Would they all just go to 1? Okay, so it would go to 2.
Yes. 1 cubed would go to
3.
Right. 1 to the 4th is going to go to 4. 1 to the 5th is going to go to 5, and so on and so forth, right? Okay. So the kernel of the homomorphism is basically, like you said, it's the empty word, but it's also 1 to the 5th. It's also 1 to the 10th, 1 to the 15th. And so
all multiples of 5.
So it's basically 1 to the k, or 1 to the 5k, where k is an integer,
Okay.
along with the empty word. Okay. So by the first isomorphism theorem, this free group on the symbol 1 modulo the kernel is isomorphic to Z5. Does that make sense?
Yeah.
Okay. Now, let's unpack this just a little bit. This free group on one element, we said, is like, we have the empty word, we have 1, we have 1 squared, 1 cubed, 1, we have 1 to the negative 1, 1 to the negative 2, and so on. What does that look like I'm writing? What if I just write this a different way? 0, 1, 2, 3.
Oh, like the integers?
It's the integers. So that free group on one letter, or on one symbol, is isomorphic to the integers. Okay? And then what does the kernel look like I'm writing? Well, we said this is like the empty word, 1 to the 5th, 1 to the 10th. And
So that would be 0, 5, 10, and then on the other side, like -5, -10.
so remember, that's what we called 5z.
Oh, right.
Yeah. So this is isomorphic to z mod 5z, which we already know this is the same, basically the same thing up to isomorphism as z mod 5, right?
Mm-hmm.
Okay. So here, this is written as these elements 0, 1, 2, 3, 4, and the addition is mod 5. Here, we think of them as cosets, right? Because this is a factor group, or a group, whatever term you want to use, but they're isomorphic to each other. And one way you can show that is by using this idea of taking a free group and finding what the kernel is. This is kind of the fundamental idea behind what we're doing. Okay, does that make sense?
Yeah.
Okay, so let me define what a presentation is now. Here's a definition. Do you have any questions?
No.
Okay, so let me think about this 1 second. Well, let X be a set. And then I'm going to let A, or X, actually, let me not do that. Let X be a set, and I'm going to define X inverse to be the set of all symbols. Okay, this I'm not actually taking the inverse of anything. It's just a formal symbol. Okay, so then I'm going to define X inverse to be that, and I'm going to let A be X union X inverse. Okay, this is called an alphabet. This is called the alphabet on X. This is one term for it. This is an alphabet on X. Now I'm going to let A star be equal to the set of all words on A. So that means elements of A star are going to be things like, X1 raised to a certain power, X2 raised to a certain power, out to xk raised to a certain power, where the xi's are elements of A. Okay, so they're elements of my alphabet. And the n sub i's are integers. So in other words, if X is equal to, AB, that means A is going to be A, B, A inverse, B inverse. Okay, does that make sense?
Yeah.
So far, okay. Because this is just X union X inverse. So all my elements of X, which are A and B, and then all the elements of X inverse, which would be A inverse, B inverse. Again, these are just formal symbols. The inverses don't mean anything yet. And so then elements of A star would be things like A, B, A inverse, B inverse, B inverse, A inverse, etc. Okay, things like that. So what we do inside A star is we define operations. So the operation in A star is called concatenation. Concatenation. That is, I just write down formal symbols beside of each other. Okay, so when I write down A and B, this is an operation in A star, called concatenation. You know what the word concatenate means, just generically? If you concatenate two things, you just write them down beside of each other.
Okay.
That's all it means. Okay.
Cool.
So just to and to simplify things, we're going to write this concatenation as A squared. And we're going to, if we ever have something like this happen, we're going to let that be a cancellation. So that's going to be what's called the empty word. Okay.
Where did I read juxtaposition?
Okay, yeah, juxtaposition or concatenation. Yeah.
Okay, they're the same.
Yeah.
Okay.
Yeah, when I learned it, I called it concatenation. Right, exactly. And it turns out this forms a group, okay? The proof that this forms a group is annoyingly long because it takes a lot to prove associativity. That's why it's so annoying. So we're just going to ignore it, okay?
Sounds great.
So this forms a group, okay? Any questions?
No.
Okay, now a new definition. So let G be a group with generating set X. Okay, that is, if I take the group generated by this set, I'm going to get G. Okay. And now go ahead and form A, which is going to be X union X inverse, and form A star, which is the set of words over A. Okay. So because of the way we wrote this, it turns out that A star is just all elements of G. And A star is closed under concatenation and inverses. So think about that for a second and see if you believe me. Well, in other words, so do I want to say this? Yeah, this is what I want to say. But what we get is that the group generated by X is also equal to A star. Oh, you know what? No, sorry. I forget all this.
Okay.
Hold on a second. I think I'm getting ahead of myself. Yeah. Okay. Sorry. Let's just forget all this. I want to go back. Nothing I said is false, but I did it in the wrong order.
Cool.
I sketched these notes out early this morning, and I think I made a mistake. Give me just 1 minute, okay?
Okay.
What am I wanting to say here? So I want to define, let G be the group generated by some set X, and A is just going to be X union inverse. So X is going to be a subset of G as sets. Yeah, this is fine. I think with the way I defined it up here. Yeah. I'm sorry. I feel like I'm overthinking this. Does what I wrote above make sense? Like, does all this make sense up here?
Yeah.
Okay. Yeah. So let's just stick with this for now. Okay.
Okay.
So let's just stick with this. So generating set G is going to be this. And then what I want to define now is a relator. So a relator of G is a word W in A star such that W is equal in G to 1. Did I lose? Sorry, I'm sorry. I took all these notes. Are they out of order? Give me just 1 second. I'm sorry. I feel
All good.
a little bit annoyed with myself right now. No, this is good. Okay, this is good. Okay. So this is what a relator is. It's an element of G that's equal to 1, basically. Okay. All right. Now, a relation is an equation. Like W1 is equal to W2 in G, where W1 and W2 are elements of A star. So a relator is something that is just the identity. Okay? It's a string of letters that just reduce to the identity. And a relation is an equation where 2 things are equal. Okay? So note W1 is equal in G to W2 is a relation if and only if W1, W2 inverse in A star is a relator. Okay, so this is an important distinction, the difference in a relation and a relator. A relation is just an equation. A relator gives you an equation, and a relator is something that's just the identity. Okay?
Okay.
All right, questions?
So we're relating this to topology, right?
We are eventually, but this at the very end, I'm going to show you how this is related to topology.
Does it have to do with something with like the loops and how like x0 and x1 are going to like equal?
It is exactly going to be something with the loops.
Okay.
Because the loops are going to give you presentations of fundamental groups. This is how you get fundamental groups in terms of this stuff. So I still haven't defined what a presentation is yet, but I'm almost there. I need one more thing to define, but that's a very good observation. Okay. All right. So G is going to be a group and R is going to be a subset, not a subgroup. Okay, it's going to be a subset of G. Okay, so we define something called the normal closure. The normal closure of R in G is this is going to be a stupid definition, the kind that you hate. It's the intersection of all normal subgroups of G that contain R. Okay? So you take every single normal subgroup that G has, and then you grab onto the ones that contain R as a subset, and then you intersect all of them together. Okay? So we denote this a couple of different ways. One way to write this is the group generated by R with G over it. Another way is to write it as R with a line over it, because that looks like closure. Okay? And this is equal to the intersection of all normal subgroups of G, where R is a subgroup of N. Another way to think about it is like this. That is the normal closure of R is the smallest normal subgroup of G that contains R. I promise we're going to get to some examples, okay? So you take a group, you take a subset of your group, then you look at every normal subgroup it has, take the intersection of the ones that contain R. That's something called the normal closure. Okay? Okay. Now I can define what a presentation is. Let X be a set. Let Fx be the, you know what free groups are? Did you read about free groups?
Yeah. Plus, we just talked about free groups.
We kind of just talked about free groups, right? So let f of x be the free group generated by the set X. Okay, it's that A star group.
Mm-hmm.
So now let's let R just be any subset you want. Okay, subset of that free group. The group defined by the presentation XR is just the free group on X modulo the normal closure of R. Okay. I know this isn't this you don't have any idea of what this looks like yet, okay?
Mm-hmm.
But when you see this notation, right here, this is what you think. I have a set, and I'm going to take the free group on that set. That's X, and R tells you what to mod out by. Okay. Now, have you done the gap exercises yet for chapter 26? Okay. So this is what you've been doing, right? You form a free group by putting in free group on 2, 3, or whatever, and then you mod by a bunch of relators, and it gives you a group. You've already been doing this. This is kind of the formal construction. Now, the elements of G equals, XR. Well, these are cosets because this is a factor group, okay?
Mm-hmm.
WN, where W is an element of A star, those words, and N is equal to that normal closure thing.
Yeah.
Okay. Now, we usually, this is where it gets kind of annoying, but this is just how it works. We don't usually write it with cosets. We usually just write W as an element of G. Okay.
Right.
But notice this can mean three things. And this is what it's like when you get into higher math. You really have to pay attention to context to know exactly what you're talking about. When you write W, W can mean three different things. First of all, W can be a word in A star. 2, W can be an element of F. W can be an element of G. It can mean three different things. So just pay attention to context. Okay. One more thing to tell you, and then I think we're going to start looking at some examples. Final thing to note, okay, W1 equal in G. That's why I was putting G under the equal sign to let you know where we're at. Okay, so we're talking about group elements in G. W equal to G. So we're going to assume that. Let's see. Well, let me say it like this. When I write this means I'm talking about in, okay? If I write W1N equals W2N, that means I'm saying that W1, W2, I'm talking about things inside the normal subgroup.
Right.
And lastly, for R in R, okay, in that set, R is going to be an N because N is that normal closure. So R in G is going to be equal to 1. So this one right here, this is the important one. Do you understand why that has to be true? I've been talking a lot, and so it would be normal if you've zoned out a few times, okay?
Well, I mean, we talked about something earlier.
Okay, so let's go earlier and see how R was defined, okay?
Mm-hmm.
This is how R was defined.
R is a subset of G.
I take a subset of G, and then to form R, this closure, I take all normal subgroups that contain R, and I intersect them together. Okay, so you know that the intersection of two groups is a group, right?
Mm-hmm.
And the intersection of two normal subgroups is a normal subgroup.
Yes.
So the closure is a normal subgroup, but it has to contain R.
Mm-hmm.
Because every one of these normal subgroups has R in it, right? So this normal subgroup contains R. Does that make sense?
Yes.
You sure?
Yes.
Okay. Well, if R is just an if little r is an element of this set, that
And it has to be
inside this closure, right? Remember what this was. This was just equal to the normal closure of R, right?
Mm-hmm.
But G is equal to this mod N. So if I mod out by it, it has to be equal to 1 inside of G because I've modded out by it.
Yeah.
Does that make sense?
Yeah.
So that means it's what? What are all things that are equal to the identity?
what are all things equal? Like
We call them,
a relator.
I know, and you're not, I don't expect you to
I mean, that's the thing I was referring to when,
Yeah.
like when I said it earlier.
yeah. So what I'm saying is elements of R are relators. These are important relators and they get a name. They're called the defining relators of the presentation. Okay, they're the defining relators of the presentation XR. So we're going to talk about group presentations. And whenever I say presentation, so when I use the term a group presentation, I do not mean a bunch of people getting together and talking in front of people, okay? What I mean is, this means I have a set X and I have a set R, which is a subset of the free group on that set X, and then I form XR, which is the same thing as this free group on X modulo the normal closure of R. That's what we mean by a group presentation. Do you have any questions?
No, but I would like to see examples.
Okay, that's the next thing that I'm going to do. Let's do some examples. All right, examples. First example. Let's take X to be the set given by X and Y. Okay.
Okay.
And let R be the set X to the fourth, Y to the third, and XY squared. Then if I write the group presentation, this is going to be the group generated by these two symbols, X and Y, modulo the relators, X to the fourth, Y cubed, XY squared. This is not some familiar group where we can say, oh, this is just blah, blah, blah group, right? I don't know, maybe it is, maybe it isn't. But this is a group, okay? You take, it has two generators, X and Y, and then we know X to the fourth is equal to the identity, Y cubed is the identity, and XY squared is equal to the identity, okay? So whatever this is, it has two generators. It's a group that has two generators. We know that. Second, we know that X to the fourth is equal to the identity. And by the way, I'm not writing E because we're doing advanced level abstract algebra. And so whenever a group is written multiplicatively, we just write one for the identity, okay? Because we're advanced now, okay? We know X to the fourth is the identity. We know that Y to the fourth is the identity. And we know that these are all equal to the identity because they are the defining relators. Okay. Yeah. But this isn't all identities. Or this isn't the only thing that can be written as the identity, because these are just the defining relators. Remember, you can't get all of them. Okay, I'll talk about that in a second. But can you tell me something else, another set of symbols that has to be equal to the identity? Just
like,
tell me something else one is equal to that is not in this list.
X squared times X squared.
X squared times X squared. Well,
which is basically X to the fourth.
By the rules of concatenation, we can write that as X to the fourth. Give me another one.
Is this what you're looking for? Like me breaking them up, basically?
Like, yeah, like, well, this is, right?
Yeah.
That's the identity, right?
Yeah.
Because X to the fourth is 1, Y to the fourth is 1, so their product has to be 1. So what I'm getting at is these aren't all of the strings of X's and Y's
Mm-hmm.
give you that are going to give you 1. That they're
Right.
okay. Does that make sense?
Yeah.
Okay. Now another example. Another example. Take just this. This is a group presentation. This is the group generated by the set X.
Mm-hmm.
It has X as the generating set, and it has an empty set of defining relators.
Mm-hmm.
This is just the free group on X. And note in this case that R is just the empty set.
Okay.
Okay, here's another one. Take a group presentation with a single generator X, a single relator X raised to the K, where in this case, K is not going to be 0. Well, this is the free group generated by a single element X, right?
Mm-hmm.
Modulo the normal closure of X to the K. What is that? Single generator X and X to the K is equal to 1. This is a familiar group.
It is.
Mm-hmm.
The
We have X, we have X squared, we have X cubed, and we have X.
like X to the 4th equals 1.
No, K. So
Oh.
what would X to the K plus 1 be?
X.
Yeah, this is equal to X to the K plus 1. This would be X to the K plus 2. So what group is this?
Is it gonna be like Z mod K?
It is. It's going to be isomorphic to Z mod K. Right? It's not. We're not going to say it's equal to it because they have different group elements, right? But it is isomorphic to it. That's exactly right.
Okay.
So X mod X to the K. This is isomorphic to the cyclic group of order K, which we know is isomorphic to Z mod K. Okay?
Okay.
Making sense?
Yeah.
We sure?
Mm-hmm.
Okay. Let's see. Let's throw a couple adjectives on there to presentations. If X and R are finite sets, we say the presentation is finite, and the group in G, which is given by this, is a finitely presented group. Have you come across that term yet?
No.
Okay, but you've been working with finitely presented group. That's everything you've been doing in GAP. They've all been finitely presented group. Let me ask you a question. I want you to think very carefully, okay?
Okay.
Are finitely presented groups finite groups?
No.
Why not? Because that's kind of the obvious answer. You're right. You're exactly right. Yeah.
Because we know that X and R is like.
Can you give me an example? take X to be, you're going to tell me this, and R to be the empty set. To give me a finite set right here, which will generate an infinite group.
So it generates an infinite group, so it like never ends.
Yeah. Well, it has infinitely many elements in it.
Could it just be like one number?
Yeah, okay. Yeah, just one symbol, right?
Okay.
So what are the elements of the free group generated by X? Well,
That raised.
huh?
So
Yeah. You start to say it. Say it.
So that'd be like a, and then a squared and a cubed. Oh, and then all the inverses in front. Yeah.
So what group is this?
The integers.
Isomorphic to the integers. There you go.
I was thinking like the integers in my head, but I didn't know what I wanted to put there for a
Of course
second.
not, because this is new. This is something that I didn't learn until like my second year in graduate school. Okay.
Okay.
So you're fine. And actually, this is not something that I ever learned in a class. This is something that I learned as part of my research. So this isn't something that you would be expected to know, but this is how you develop your intuition. Okay.
All right.
Now, finitely presented groups are not necessarily finite groups. However, this is as a theorem, proposition, whatever. All finite groups have finite presentations. Okay, because they're just finite groups.
Yeah.
Okay. All right. Let's see here. Do you have any questions?
No.
You sure?
Yes.
Okay. Let me give you just two more things with group theory, and then we'll look at how this is related to topology. Okay. I hope that you're not getting annoyed, because I know that you're not a big fan of algebra so far.
I mean, I'm not getting annoyed. Okay.
Are you confused, or you feel like it's too hard, or what?
I mean, this was like the first part of the algebra that was complicated. The gap made it more understandable. Mostly because it would do it for me.
Of course. Well, look, the Gallien's presentation of this is a bit confusing, because he's giving you every single little detail and proof and all that stuff, which is why I wanted to take an hour and go through this to try and simplify it some.
Yeah.
Go ahead.
Yeah, the topology is like really complicated for me though.
Yeah.
Yeah.
We're gonna get there. Okay.
Okay.
So, one more bit of terminology. A commutator is a relator of the form A comma B. So we put it in brackets, okay, because it's something special. But all it is just A, B, A inverse, B inverse. Okay?
All right.
Now note that a commutator is equal to 1 if and only if A, B, A inverse, B inverse equals 1. But that means that AB has to be equal to what?
A inverse, B inverse?
No.
No. 1?
No. No. No, you're panicking a little bit. Think about it. If AB, A inverse, B inverse is 1, how would I get rid of the B inverse here on the right? What would I do? Multiply by what?
B.
Okay, so I want that go. Okay. So if I multiply by B on both sides, A, B, A inverse, B inverse, B, equals 1 times.
Oh, is it gonna be like BA?
Yes, that's it. Yeah. Yeah. So AB is going to be equal to BA. In other words, A and B what?
Commute.
Commute. That's why it's called a commutator.
Oh, that makes sense.
So in other words, A and B commute. So if you want to make a group a BON, you mod out by the commutator because that makes everything commute.
Mm-hmm.
So for example, take a group generated by A and B with the single relator, the commutator A and B. Okay. What group is this? Well, this is the same thing as the group given by AB such that AB is equal to BA.
Mm-hmm.
What group is that? So it's a group with two generators, okay? And they commute with each other. Can you think of what group that is?
Is it gonna be like a dihedral group?
No, because the dihedral group has a lot more defining relations.
Yeah, okay, that's true.
If you rotate it 4 times around, you'll get where you started. This has only one relation, that A and B commute. Well,
it only has two generators.
It has two generators. So the group generated by A, just A with no other relations, is going to give you a copy of the integers.
Yeah.
Right. So this is generated by A. The group generated by B is going to give you a copy of the integers. This one is generated by
be the integers.
What?
Is it also going to be the integers?
Yeah, and so it's the direct sum. Do you know that symbol direct sum?
Yeah.
Okay. So that's what the group is.
Okay.
So it's the group that has so Z plus Z is, I mean, as a set, it's like this, right? All A and B.
Yeah.
Or A and Z, B and Z. But it commutes. So A1, B1 plus A2, B2 is equal to A2, B2 plus A1, B1, which they're both equal to A1 plus A1, comma, B1 plus B1, 2, which is equal to A2 plus A1, comma, B2 plus B1. That's what that group is.
Yeah.
Okay, well, what's this one? What group is this? AB with the relation A to the fourth and the commutator. What group is it has two generators.
Yeah.
You know the generators commute.
Yeah.
Okay. And what's this going to tell you?
That A to the fourth equals 1.
Okay. So what group has that property? One generator and A to the fourth is 1.
D4 has that property.
Like but
more generators, like
it has D4 has more relators and generators, right?
Yes.
So what group has one generator and one relation that A to the fourth equals 1?
Z mod 4.
Z4. There you go. There's one of them. And then what's this other generator tell you? That's going to give you what?
Z.
Z. And
we add
the commutator says you can add them, right? That's
it. Okay.
Okay.
Yes.
What would this be? A, B, C. Okay.
Okay, so 3.
A, B, A, C, B, C, B to the fourth, C to the seventh.
Okay, so Z.
Why?
Because A, so there's the generator A, and there's no problems with the A, or Related.
So let's be precise. When you
There's no relators.
you mean there's no other relators? Exactly.
Okay.
Yes, very good. Okay, what else?
Plus Z4.
Okay, so Z4 comes from what?
B to the fourth as the
Okay.
relator.
Okay, and then you said plus. Why is it circle plus?
Because it commutes.
Because it commutes with A. Okay, and then is that all of them?
No.
What
And
else is there?
then we add Z7.
There you go. Very good. There
Okay.
you go. Good. Now, what I'm building up to here is an extension of a theorem you saw in abstract algebra, which is really important. So I'm going to write it in green. Okay, and this is
The fundamental theorem of abelian groups.
right, but in this case, it's not just not abelian groups. You're close. You're close. The fundamental theorem of finitely generated, right? I think in abstract algebra, you learned the fundamental theorem of finite abelian groups.
Yeah, that's what it was.
Yeah. Now we're going to do finitely generated abelian groups, which a group is finitely generated if it's generated by a finite set.
Okay.
Okay. The fundamental theorem of finitely generated abelian groups says if G is a finitely generated abelian group, then G is isomorphic to Z raised to the R power.
Mm-hmm.
And then I think sometimes they use cross, and sometimes we use plus. I'm going to use.
Does it matter?
It doesn't. Okay, that's a good question. It matters if you have an infinite product that goes on forever.
Okay.
But if you have a finite product, they're the same.
Okay.
We're only doing finite because they're finitely generated. So then Z mod P sub 1 plus Z mod P sub 2 plus ... plus Z mod P sub K, where there's different ways to write these, but I'm going to say that the PI are prime.
Okay.
But there's other ways to formulate it, okay? This isn't the only way. Well, shoot,
But
primes that have two powers.
are they prime? Because like we did
You can,
Z4 up there.
huh?
We did Z4 up there.
Right. So notice I put those ends so you can write them as powers of primes.
Oh, okay.
There's another formulation of this which is equivalent, where you say that, so you would do Z mod N1, Z mod N2, Z mod N3, where each one of them divides the other one. So you can like write them increasing order, but this is fine, okay? R, sorry. Oh, no, I'm gonna do that. Z mod R, or excuse me, ZR is the free part. That's called the free part of your group, okay? That's because it's free of any relations, okay?
So like Z.
Exactly.
So like what we did with the A. Okay.
Yes, exactly. Z and R is called the rank, okay? All of these terminologies are going to come back to haunt you, which is why I'm writing them, okay? Z P1 N1 plus Z P K NK is called is the torsion part. Torsion means, the word torsion means twist, okay? So think of these things come from the relations in the presentation that kind of twist it back around to the identity.
Yeah.
That's how that comes from, okay? All right. We're going to use this a whole lot for the second topology part.
Okay.
Now,
is this the thing I should prove?
No, this is already done. This is something you're going to use.
Okay.
Okay. Now, but this is fundamental, okay? Now here is an annoying fact. Okay, this is a stupid,
Okay.
annoying fact. Okay,
Love that.
yeah. Given a finitely presented group G
Mm-hmm.
and a word W in G, it is impossible in general to determine if W is the identity element. This is something that it's been proven is impossible to calculate.
Cool.
If you want to read about it, this is called the word problem.
Ha 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 ha
Yeah.
ha ha.
What?
It's a pun.
Kind of, yeah, but kind of not, right? I mean, you know, when you take college algebra, students always say, I hate word problems. Well, I can say to them, I hate the word problem too.
Mm-hmm.
But Google it and read about it. You'll have to put the word problem for presentations or something if you want.
I hope that I get a bunch of stuff about word problems in presentations.
Yeah, that'd be cool, right? So part of my dissertation research and the research I've continued is I've tried to solve this in special cases. I try to solve the word problem. And when I go into it, I don't know. Here's the thing. When you say it's impossible to know in general, if I give you a group and a word, you don't know if you can solve it or not. Okay?
But maybe you can. And it'll
Maybe
take
you
a really
can.
long time to figure it out.
Yeah, but here's the thing. Just because you don't solve it doesn't mean that it's impossible. Maybe you could keep working at it and you would solve it in like 1,000 years.
Oh, that's exciting. Okay.
So when you solve it, you have a solvable word problem. But if you don't solve it, you don't know.
Okay.
So that's why it's an annoying fact.
So it's just
Okay.
impossible to determine it. Okay.
Yes, it's indeterminate. This is what we may do next semester as part of some of your publishable research. Okay. Now, you have like 10 more minutes or you need to go?
No, I got time.
Okay. So how does this relate to topology? Okay. Here's how this relates to topology. Let's take space X, which is going to be S1 wedge S1,
Okay.
which if you remember what that is, you take the circle and another circle, and you're going to stick them together at a common base point.
Okay.
Okay? So we've talked about loops, right?
Mm-hmm.
So I can take a loop alpha going that way
Mm-hmm.
and a loop beta.
Mm-hmm.
This is my common base point, x0.
Yeah.
How far have you read in topology now?
6.3. I've read through 6.3.
6.3. Okay. Okay.
And it was rough.
Yes.
I'm really having a hard time here.
Okay. Well, we talked about that some last time, right?
Yes.
Okay. So without going into the details again, all right, just modulo the details. Loops form a group. Do you believe that loops?
Yes. Loops form a group.
In particular, homotopy classes of loops form a group. Okay. So let's take the class given by alpha, by this loop alpha. Okay. Well, what's going to be in there? I'm going to have the constant loop at x0, anything, right? And I'm going to have alpha. I'm going to have alpha. So this is alpha 1. Do alpha twice, where I travel along the loop and travel along it again. And then I want to call this, let me write it like this. I'm going to say alpha at 0. So it's a constant loop right there. Then I have alpha cubed. And then, or I can go backwards along this loop. So
So it's like the integers.
it is the integers, right?
Mm.
So remember what a loop is. It's a function from 0, 1 into this space somehow, right?
Mm-hmm.
So alpha inverse would just be alpha of 1 minus t. So that makes you travel backwards.
Yeah.
And then I would have alpha -1, which is going backwards, alpha -2, and so on. So like you said, this is isomorphic to the integers. What would class of beta be?
The same, but with beta.
Okay. So beta -1, beta is
Like 0.
yeah, beta like that. Beta 1, beta 2, and so on. This is isomorphic to the integers.
Would we write it as z plus z? Could we
That's
do
a
that?
that's a good question. So the question is, do they commute?
That is the question.
That is the question, okay? So the big question is, do they commute? I'm not going to answer it yet.
Okay.
Because now I want us to look at x equals the torus. Okay. Now the torus can be written, we talked about this before, as S1 cross S1. This is the torus. And remember, this can also be written as this square. Where these get identified and these get identified. And this is filled in, okay? Imagine 2 loops on here, okay? Imagine a loop going this way. Okay, so that would correspond to a vertical loop. Okay, and imagine a loop going this way. So right here, the intersection is going to be their common base point.
Okay. And that would be a horizontal.
This would correspond to a horizontal loop. Okay, I actually labeled these bad. I meant the A's and alphas to match up, but whatever. Okay, now let's look at, well, okay, we could do the same thing. We could do class of alpha, and that's just going to be isomorphic to the integers. We could do class of beta. That's going to be isomorphic to the integers. And so the question again, it's the same question you had before, right? Do they, is it z plus z? So the question is, do they commute? Okay. Okay, now we're getting to the nitty gritty stuff, all right? I want to show you a video real quick.
Okay.
Okay, can you see this?
Yeah.
Okay. All right, so this is a square that's going to get, or a rectangle that'll get folded down to form the torus, okay?
Okay.
Now, this, I wish they'd colored them differently, but they didn't. But pay attention, I have a vertical line, which when I make the fold is going to give me a loop. And I have a horizontal line, which when I make the fold is going to give me a loop. Okay? These loops commute if I can deform traveling vertically and horizontally into traveling horizontally and then vertically. That's what we mean for loops to commute, okay?
And the torus does compute.
Right. Okay, now so watch the picture. So look, this is a homotopy, right? Forming it to a loop where now we can travel, you can't see my finger. Now we're traveling vertically and horizontally and then vertically. So you see how it's going back and forth?
Yeah.
So now it's going to turn it to the torus. Well, okay. So it's kind of deforming into the torus now. And so there's those 2 loops. Okay, now watch. Now it's going to twist it to the other way. So the first picture I had was vertical, horizontal. Now it's deforming it to the same exact loop, but this time it would be corresponding to the vertical, horizontal. So it's going to unwrap again, I think. Okay, yeah, so it's going to unwrap and it's going to be the other way. So just watch. Oh no, shoot, it's not unwrapping. It's doing the homotopy there again. It's going to unwrap after this.
Okay.
Oh no, it's just homotopy again. I'm sorry.
It's all good.
You kind of get the idea?
Yeah.
Okay. Because, so starting out, we are traveling. So going up in, can you see my mouse?
Mm-hmm.
So this would be a loop when we fold down.
Yeah.
This would be a loop when we do it this
We-
way.
Yeah.
And then we can continuously deform that with a homotopy to get this, which would be a loop traveling this way and a loop traveling this way.
Mm-hmm.
So because we have all this space to move around in, the answer is, for the torus, the answer is yes.
So then can we say that the torus is isomorphic to Z plus C kind of thing?
It's exactly right. Now,
Okay.
here's how we write that, okay? This is equal to a group that has generator AB,
Mhm.
where A is going to correspond to this class, B is going to correspond to this class, with the defining relation, the commutator, okay?
Yeah.
And the reason I'm writing it like that is because the generators of the fundamental group are explicitly the homotopy classes of loops. So that's how you calculate fundamental groups, is you take all the loops and those are your generators for your presentation.
Okay.
And then any relators you get from deforming homotopies, those are the relators in your presentation. So this is Z plus Z. Okay.
Okay.
Now let's go back to this one. Okay. So imagine, let me put some more space in, hold on. And we're almost finished. 'Cause I've not had lunch and I'm really hungry.
Yeah, I mean same. So.
Okay. All right, but we're almost done. Okay, so let's write S1 wedge S1, which is the circle, wedge the circle,
Mhm.
and give it like this, okay? But is this what I want? I want to do, yeah. This is the only thing that I have, okay? This is A. Nothing in the middle, okay? There's no surface there, okay?
Okay.
I can deform this to be something like this.
Okay.
And this is going to be my base point. So I'm going to, oh, sorry, no, this is incorrect. I'm sorry. No, sorry. This is actually, hold on. I take the loops, stretch them out. So I want to take it like this, stretch it out this way, and then unroll it. So I'm going to have this unrolled. So these are going to get identified. This is going to be, I'll call this B, and I'll call this C. Okay, yeah, like that. And there's nothing in the middle.
Okay.
Okay, so once I fold this down, right, it's going to turn into this. And then I can collapse this middle part. I can collapse this red part together through a homotopy to get my space S1 wedge S1. Do you see how that progression grows?
Yeah.
First thing I do is I fold it up. Okay, so I start at the bottom and I fold it up, and I get this. Then I can define a homotopy that'll just collapse that interval to a single point. Do you see that? Do you? Be honest.
No.
No. Okay. So imagine that I have something made. I have 3 sticks of, or three things of Play-Doh, 4 things of Play-Doh that I've wrote out into logs. Okay.
Okay.
So I have a piece of Play-Doh like this, a piece of Play-Doh rolled out like this, a piece of Play-Doh that I'm going to put right here, and a piece of Play-Doh that I'm going to put right here. Okay.
Okay.
So I can take my Play-Doh and I can, oops, I meant to do black. I can take my Play-Doh and I can do this. So I'm going to like squeeze these points together so they're not going to come apart. And I'm going to fold this top part down so that I get something like this. I'll have this, and I'm going to squeeze those points together, and I'll have the green one. Oops. I'll have the green, oh, damn it. Excuse me. I'll have the green loop over here,
Mm-hmm.
and I'll have the blue loop over here, but the 2 red ones,
Are together.
I've smushed them on top of each other. Okay?
Oh yeah.
Makes sense. Then from there, I'm going to take the red one and I'm
And
going
push
to
it together.
smush it together. Right. Smush it together. So the red one is just going to be a single point.
Yeah. Okay.
I guess red, if you want to see it that way, that'd be better. But then I'm still going to have
Your blue loop and your green loop.
my blue loop and my green loop, right?
Yeah.
Okay. So once I've done all my smushing and bending, a loop inside of my space has to come from the green or the blue.
Mm-hmm.
Do you see that? We've been going for over an hour, so if your brain's shutting down, it's okay. All right. So that means loops have to be traveling to over here or over here. Okay. There's no way to turn one into the other. Do you see that?
Okay.
Because
Yeah.
I don't have anything in the middle, so I can't deform one into the other.
So they don't commute. Is where
It does not commute.
Okay.
So the answer is no.
So then, can we not like relate it?
So that means that the fundamental group of S1 wedge S1, well, I do have a copy of the integers because I have a loop,
Mm-hmm.
another copy of the integers, but this is the operation.
Okay.
This is what's called the free product.
Okay.
So this is going to be equal to, if this is generated by A, this is generated by B. It has presentation A and B, and then no relator. So it's things like A, B, A squared, B cubed, B squared, A to the 100.
Mm-hmm. A
Things
lot.
like that. A lot. Yeah, it's an infinite group, so it's a free product.
Yeah.
So, okay. Once you go through that stuff in the book, it'll make more sense. But that is our primary focus now, is the topology.
Okay.
Okay. I'm sorry this took so long, and I'm sorry I threw so much at you.
It's all good.
This is probably the least enjoyable session we've had so far. All right, I'm going to stop the share, or stop the recording.